Notwithstanding the interesting geometric sources for sine and cosine, they're most often used in other applications, not because of geometry, but because they're one of the few families of functions that we know that oscillate, that go up and down, that repeat themselves. Quadratics, cubics, exponentials don't do that. So we're going to study a little bit of how we can adapt the sine and cosine functions to build functions with other properties that we might want. In particular, let's talk about shifting and scaling of a trigonometric function. Take a look at the function here, y equals 10 plus 4 cos of x, and ask yourself which of these graphs here represents the graph of this function here. Okay. Hopefully, you remember back to the first week where we talked about vertical scaling. If we have a 4 out front of cos of x, then we have a vertical scaling factor, and we also have a vertical shift. And if we remember the baseline for cosine by itself will oscillate between 1 and -1, so this is cos of x. If we look at another version, which would be 4 cos of x, ignoring the periodicity here, I didn't quite sketch that to horizontal scale, but with the same basic pattern, we'd have 4 cos of x, and then the shift would increase everything. In particular, it will increase the center of the oscillations from 0 up to 10. And if it goes from 0 to -4 before, it'll go from 10 down 4, from there to 6, and up to 14. And that will be our cycle here for 10 plus 4 cos of x. And with that idea in mind, this one here looks like the graph that would work. This has too large an amplitude. This doesn't go in the right direction because it starts the wrong direction. Cos always starts high and goes low unless it's flipped somehow, which it isn't here. And this pattern here is close, but the amplitude of the oscillations is too small. So B here is the correct answer. In terms of terminology, when we talk about the 10 and the 4 here, using sine and cosine is so common that we have special names for the scaling. So the amplitude here is 4. It's worth noticing that the total variation in the graph is actually +4 and -4, or 8 in total. So if we look at this graph here, it goes up to 4, it goes down to -4. We call the amplitude the distance away from the average. And the average value, as we just said, would be 10. Usually the average of a cosine is 0 because it goes positive, then negative in perfect balance. But if we include a shift of 10, then the average value moves up to 10. So amplitude of 4 means we go 4 above and 4 below that average. All right, so that's scaling and averaging. How about period and phase? How can you find the period of the function cos of a times x? Well, recall, before we can talk about the period of some modified version of cos, we have to know what the period is already for the cosine graph. And both the sine and cosine graph share the same period. Let's talk about the the cosine graph here. One full period takes 2 pi radians to complete. So that's one full cycle. And you can think about that in the circle interpretation. It takes 2 pi to complete one full cycle, 2 pi radians to complete one full cycle around a circle. Okay. That's when it's just cos of x. When we have a multiplier like ax, what we also need to recall is that multiplying by a inside produces a horizontal compression if a is greater than 1. So if we put a 2 in here, what would happen? Let's do an example. Let's say we had cos of 2x. Well, what would happen there is x doesn't have to change as much for us to get an input as high as 2 pi. In fact, let's do a little sketch down here to compare. The cosine graph, when we plug in x equals pi into this function, would effectively be at 2 pi in the original graph. So things would be compressed horizontally, inwards, by a factor of 2, or things would happen twice as quickly. And so the period is 1/2 of the original. And so that means in general, our period can be calculated based on a 1/2 the original, or just pi. In general, the period will be 2 pi, our original period, divided by whatever this multiplier is, divided by a. If the multiplier in here is 2, we divide by 2. If the multiplier in here was 1/4, we would divide by 1/4 and get a longer cycle. But that a represents the level of horizontal compression or stretch, and we can change the period based on that compression or stretch of the period itself. Last thing is to look at the idea of phase. So if we're talking about shifts, and we talk about the graph of cosine again, we might want the graph to start later. And we might want it to start at some later time b. Let's take a look at this cos of ax plus b and ask, where is this peak going to happen? Let's do this in a different color just for the sake of argument here. And ask, where does it start? So if that's cos of ax plus b, this starting point is, let's call it x0. Well, what we do know is, we know cos of 0 is equal to 1. So the start of the cos graph, this point here, is going to occur when the input to cos is equal to 1. Sorry, is equal to 0. Clarify that for a second. If we plug a 0 into cos, we get a 1. If we plug some value and we want to know where the 1 is, we need to know what the input was that gave rise to that peak, that highest value. When's that going to occur? When ax plus b equals 0. So when the input equals this, we'll get a value of 0, or to simplify, minus b is equal to ax, or x is equal to negative b over a. And that would be our x0. I should put that all the way through here. Whatever our intercept or our starting point is, what we're going to call x0, when x0 is minus b over a, that when we plug it into here, minus b over a, we're going to get everything canceling. We're going to have an input of 0, and the cos of 0 will give us our peak. So it's a bit of a backwards invert way to go about it, but this is the most reliable way. Because keep in mind, sometimes these functions are written as products like this instead of the completely expanded version here, and that sometimes complicates things for people when they're getting started. So the easiest way to find out what the shift is to set the inside here, whatever it is, equal to 0. Whatever x value that is, that's the x value that's going to give you the peak in the cos graph. Let's do an example here for illustration. Some things are really easy to determine. So scanning across here, the vertical shift is the average value. we'd have a cosine graph shifted up by 5. The average is usually 0. Now it's been moved up by 5, so the average is 5. The amplitude is the next easiest thing to see. It's simply 8. It's the multiplier out front of the cos. All right, the last two things here. This part here, we can write it in two different ways. It could be written as pi x minus 1 or pi x minus pi, whatever you like. I think this one gives us the period more easily. And we just remember that rule, the period is equal to 2 pi divided by the inside multiplier. We called it a before, but it's always risky to give names to those things. 2 pi times the inside multiplier, 2 pi over pi. So the period would be 2. Last but not least, what's the phase or what's the start point? The inside is pi x minus 1 equals 0 when x equals 1. That's pretty clear. If I make 1 minus 1, I'll get 0. So that would be our phase. We're going to be shifted to the right by 1. Okay, so those different calculations make sense, especially the last one. This is the one that most students struggle with. Then you'll completely understand how to define a sine or cosine function that has the desired properties that you want about period, amplitude, the average, and the starting point for it, or what we call phase. We're just going to do a quick sketch of it. And we'll do a little confirmation here. So we had, let's sketch it and then we'll do the confirmation. So we have an average of 5, so that's the starting point, along with the phase, which said we right shifted by 1. So let's put some labels on here. 1, 2, 3, 4, 5, 6. All right. So we have an upward shift by, let's call that 5. We had an amplitude of 8. Amplitude of 8. So that means we're going to go plus 8 up and minus 8 down. So let's say that's 3, negative 3 there, and that's 13. We'll put some dotted lines in to give us some guidelines. And cosine starts at its peak. So it would start at the peak at what we said was the shift, which was 1 time point. Next, or last, hopefully, second last, we're going to need another anchor point. The period is 2. So after 2 units, we're going to be back where we started. And after 2 more units, we're going to be back where we started. Halfway through that cycle, we're going to be at the negative end, or the opposite end. We're going to be halfway through the cycle. We're going to need another reference line here. And at a quarter of the way through, we're going to be at those average values. Okay. So I think that gives us enough to sketch with. Let's try. There we go. And this would be our shifted, scaled, re-averaged, all of that factored into this graph. Just to give us some reassurance, it's worth doing a quick comparison of some of the values. So let's put x and y here. Our function was y equals 5 plus 8 cos of pi times x minus 1. So if we were right with our analysis, we should be able to plug nice integer values into the function here and get nice values back. So x of 0 would be cos of negative 1 here, but negative pi. All right, most people aren't too fast with that. So let's go to the 1 point here. Here we see we're going to have cos of 1 minus 1, or that's cos of 0. And cos of 0 plus the other bits, so 5 plus 8 times that. That's just going to give us, sorry, cos of 0, yeah. 5 plus 8 times cos of 0, and that's going to give us 5 plus 8, or 13, because cos of 0 is 1. Oh, that's exactly our starting point that we talked about. If you go and plug in x equals 2 in this function, you're going to get cos of pi. Cos of pi is negative 1, 5 minus 8 is minus 3. And if you continue that pattern, plugging in values into your calculator, because of this pi multiplier, we get nice integer x values that give us nice integer y values, and that will generate the graph that we have here. This can be pretty tedious though, especially if you didn't have a nice scaling factor like pi for the shifting or for the horizontal side. So that's why we rely even more on these particular properties when we're talking about sine and cosine functions, because they give us the graph with just a very light analysis compared to the tedium of plugging in lots of points and trying to sketch a graph. In fact, we get more detailed information from the amplitude, period, average, and phase, because we get every detail of the function from those, rather than just a sketch which is what we would get from subbing in values like this mechanically.